Hey, welcome. Today, we are heading out on a cosmic detective mission. And our targets? Asteroids. Now, these aren't just giant rocks floating out there in space. Think of them more like ancient time capsules, perfectly preserving all the chemical clues from the birth of our solar system, like 4.6 billion years ago. So let's start digging in. And that's really the perfect way to think about it. Every single asteroid is a piece of this grand cosmic puzzle. Some are dark and full of carbon, others are stony, and a few are all shiny and metallic. By learning how to read them, we can start to piece together this incredible story of how everything around us, including our own planet, actually came to be.
Right, that's the million-dollar question, isn't it? I mean, it's one thing to have a puzzle piece right here in your hand, but it's something else entirely when that piece is hurtling through the vacuum of space. So how on earth do scientists pull it off? How do they read these space rocks from such an unbelievable distance?
And look, understanding these pieces is about way more than just satisfying curiosity. It's fundamental. By classifying these leftovers from the dawn of time, we get a direct look into the raw materials that built the planets. We're essentially looking back in time to the solar system's very beginning. So let's get into our main detective tool. To solve this puzzle, scientists can't exactly just pop over and visit every single asteroid. So instead, they've become masters of deduction, using the one thing that travels across that huge void of space and carries secrets with it: light. The key technique here has a bit of a fancy name, spectroscopy, but the concept of a fingerprint on this slide is what's really brilliant. Just like no two human fingerprints are exactly the same, no two materials reflect light in quite the same way. So, by analyzing that light, we can figure out what minerals are on an asteroid's surface without ever having to leave Earth. It's amazing. So, how does this actually work in practice? Well, it's a beautifully simple process, really. First, sunlight, which has all the colors of the rainbow in it, hits the asteroid. The material on the surface, depending on what it's made of, soaks up certain colors. The light that doesn't get absorbed gets reflected back out into space, and our telescopes on Earth act like these giant eyes, catching that reflected light, breaking it down, and revealing that unique fingerprint of missing colors. And that's how we get our first huge clue. Okay, so using this light decoding technique, scientists have been able to sort the entire asteroid population into these distinct families, or types. You can think of these as our main suspects in the whole story of how the solar system was formed. So, who are the key players? Well, the huge majority, a full 75%, are what we call C-type asteroids. These are the dark, carbon-rich ones that pretty much dominate the outer asteroid belt. Then you've got the S-types, the stony ones, which make up about 17%. And that last 8% is a mix of other really fascinating rarer types, including the metallic ones. Now, to make this a little easier to remember, planetary scientists have some fantastic analogies. The C-types, which are full of carbon, organic molecules, and minerals with water trapped inside, are kind of like a soggy fruitcake. The S-types, made of stony silicates and little bits of metal, are like gravelly sand. And the M-types, which are almost pure iron nickel, are basically giant cannonballs that were forged in the cores of ancient shattered worlds. Now, spectroscopy is an absolutely incredible tool, but it's still an educated guess from millions and millions of miles away. So how can we be sure our deductions are actually right? Well, sometimes the evidence doesn't wait for us to come get it. It comes to us. And this is where meteorites come into the picture. These are actual fragments of asteroids that have survived that fiery trip through our atmosphere and landed right here on Earth. They are the ground truth, the physical proof that lets us hold a piece of an asteroid in our hands and check if our long-distance analysis was on the right track. And the matches, they're just remarkable. The light fingerprint from C-type asteroids perfectly matches the makeup of carbonaceous chondrite meteorites we find, which are packed with water and organics. The S-types match our most common meteorites, the ordinary chondrites. And that bright, featureless signal from the M-types, it's a dead ringer for pure iron meteorites. This is how we build real confidence in our cosmic classifications. But what if we could close the case entirely? What if we could pick our own suspect, travel all the way to the scene of the crime, and bring back a pristine sample for analysis? I mean, that's the ultimate step in this whole investigation. And that is exactly what NASA did with the OSIRIS-REx mission. It was this incredibly high-stakes, super precise operation. The target was Bennu, one of those soggy fruitcake C-type asteroids, and the goal was basically to pull off a cosmic heist, touch down on its surface, and snatch a sample of its ancient material. After a journey of billions of miles, this is what the mission brought home in 2023. A little over 120 grams, just a handful of dust and rock. I know it doesn't sound like much, but to scientists, this tiny sample is more precious than gold. It's a completely untouched piece of the early solar system. So what secrets was this handful of dust hiding? Turns out it was an absolute treasure trove. The analysis confirmed our soggy fruitcake theory in the most spectacular way, finding tons of water and the organic molecules that are the building blocks of life. But it also threw us a curveball, carbonates that suggest ancient hot springs might have once existed inside Bennu's parent body. So this single sample didn't just confirm what we thought, it made the whole story so much deeper. So we've seen how we read these space rocks, from analyzing their light to studying their fallen fragments to even going out and touching one. But let's bring it all together. Why does all this cosmic detective work matter so much? Because these aren't just rocks, they are the actual blueprints of our solar system. By classifying them, we can map out where all the different materials were located billions of years ago. It helps us answer some of the absolute biggest questions we have. How did rocky planets like Earth even form? Where did all of our oceans come from? And could asteroids have delivered the essential organic ingredients that sparked life on our world? You know, every asteroid we classify, every meteorite we study, every single sample we bring back adds another critical piece to that grand puzzle. And it just leaves you with this really exciting thought. As our technology gets even more advanced, letting us read these ancient rocks with even better clarity, what other profound secrets about where we came from are just out there, waiting to be discovered?